Yeah. He says it's that supplemental book. What that is? I don't know. Maybe that's his log.
I know like this.
Things are great.
Actually, I'm confused. Are the info labs group labs, but the formal or individual?
I think all the labs are group. I don't want to do formal by myself.
Let me ask him because in here it says you gotta turn one individually.
Oh, it's nice.
See, each person will turn in a draft of the lab. Because I'm thinking, I'm like, but each group will turn in a final version.
Okay. Here's one thing that I promised I was going to write on the board. This is how you access the supplemental text. Okay, so PearsonLabandMastering.com, North America. Okay, username PacNorthwest1@Pearson.com, Washington 2016, capital W, right? Okay, so once you log in, it's going to look like a course, okay, and it's going to be an empty course, okay, but one of the tabs it'll have will say e-text. You click on the e-text and you should get an image of this book, yeah, and then you can access the chapters in that book. Got it?
You don't have a PDF of that, do you?
No.
Because that would be nice.
That would be nice. They didn't give me one.
Okay.
They actually, the first thing they said was, we'll get you a PDF of it. And then they said, oh, well, we can get you this. So, sorry.
Okay.
Okay. It does sort of mean you got to be connected and read it page by page, I think. I don't, but,
Okay.
okay. Anyway,
Yeah.
that's what I got. When you're connecting with the Mastering Physics, this is the course ID. Okay, I will post all of these in the announcement sections on Canvas. Okay, so, but if you want them now, just in case it takes me.
You only have one thing assigned right now, and it's the intro, and it was due last week. Do we have to do that intro?
No, you don't need to do
Okay.
the intro. Was it assigned on this?
For the Scott, the
Mastering
Mastering
Physics,
Physics, yeah.
Nothing else shows.
Yeah. And
It doesn't show the chapter 14 stuff we were doing before?
no.
Thank you for letting me know. I will try and figure out why you can't see that. In fact, I kind of want to get on with other things, but if some of you are interested, I might like stay for a minute after class, especially someone who has a laptop, and let's see if we can troubleshoot this and get this going. Okay, because I thought those should be visible. Okay. The other thing that was talked about while people were out was that there were a number of people that were concerned about getting the homework done by Thursday night, and because of work schedules, okay, and the fact that they're working during the week, they have more time available on the weekend. It is not a significant issue for me to move the Thursday night due date of the first homework assignment to Saturday night, okay? Especially if it's not visible right now, it might be better to move that along. But hopefully I can get it visible. I will get it visible soon, okay? And then now, well, the other thing I will do, the question was, well, if you always work during the week, can we make all the homework assignments due on the weekend? And the problem is that we've got a lot of different chapters, and always getting the feedback over the weekend means that sometimes we'd go through 2 chapters and a piece of the supplement, and you wouldn't get any feedback until the end. You look like you're going to ask a question.
Oh, I was just going to propose the due date of like Monday at 5:25.
Monday
Yeah.
at 5:25,
Yeah.
like right before you come in here?
Yeah, to finish the previous week's homework.
Here, so let me finish. Okay? Because we've got all these things sort of backed up, and because I want to get the feedback to you when it's relevant, I'm thinking the next assignment is going to be, we don't have any class on Monday, but it'll be Tuesday night. Okay? Based on things that we did on Tuesday and Thursday, or well, maybe it'll be Thursday night, but it's going to be coming along, and in fact, so what I will do is I will try to be sensitive to getting the feedback early and giving you time to do things, but and post the remaining homework assignments up until the first exam by Wednesday night. Okay? And then before exam 1 is done, get the homework up for exam 2, so that you, if you've got whatever it is with your work schedule, if you know ahead of time, you can do a little work ahead or whatever. Okay? Okay, that seems to me the best way to balance those things out. Okay, so earlier tonight we were talking about different types of motion, and the fact that we had talked about oscillating motion, or we talked about constant acceleration motion or constant velocity motion before, and those motions, hopefully we know pretty well, right? We had acceleration. Okay. And we had some formulas that described, we went through a lot to sort of derive some equations of motion. Okay. And so we had things like this. We had x is equal to x naught plus v naught t plus 1/2 at squared. V is equal to v naught t, v is equal to a, v is equal to v naught plus at, and a is constant. Okay, and sometimes that constant was 0, in which case v was constant, and this was our formula for motion for a particle that was moving under constant acceleration. We talked about graphs. We made acceleration graphs and velocity graphs and position graphs. And we were able to recognize from the graphs that this type of motion was going on. Okay, so the motion that we want to talk about now is oscillating motion. Okay, so it goes back and forth. Okay. Examples of oscillating motion?
Pendulum?
A pendulum. Okay, what's a pendulum?
Damn, Les. You're not strong.
I'm listening. What pendulum is?
It's just an object hanging from like a string.
An object hanging from, oh, in fact, I've done this. Pendulum, yeah? Okay? It goes back and forth. Yeah? Okay? Cool. Other motions?
Springs.
Springs? What about springs? How do I make the oscillating motion?
Touch a mass or an object.
Attach it. Okay, I'm attaching a mass to the spring, and then what? Drop it? Yeah. Okay, so this is also going back and forth. Other motions?
Boomerang.
A boomerang. A boomerang. I don't have one. Okay? But, so the idea with the boomerang, right, is you've got, do you mind if I use your frisbee as a prop?
Yeah,
I
yeah.
promise I won't use it as a boomerang because I
You
can't.
can throw
Okay?
as hard as you
No,
want.
okay. But a boomerang, you take your boomerang, okay, and you throw your boomerang, and what happens?
Comes back.
Goes back.
It comes back, but it goes out and it turns around and comes back. Okay? Good.
You can do that with a frisbee.
I think you can. I think you vertically you can get it to do that. I don't think I can do that in this room. Okay? Have you tried?
Yeah, I know. You can look lonely and like play frisbee by yourself.
Yeah.
By throwing it up high enough
Oh,
at an
you can
angle,
do
it'll
that
just come
and have it
right,
come back down.
right back to you.
Yeah. So that's an oscillating motion, right? It goes out, it comes back, goes out and comes back. Okay? Others? A swing, which is kind of like a pendulum. Okay. I had this one in mind. Okay. Right. You've got a tennis ball, right? And I throw it on the ground. I have to do this right. Yeah? So it goes down, comes back, goes down, and comes back. Okay? So that's what it takes to be an oscillating motion. It goes somewhere and comes back to where it started. And then ping pong balls do it too. And it repeats the pattern. Okay? So if we were going to describe that, we would need to, well, over here, we describe things with position, velocity, acceleration. Do those things have position, velocity, acceleration?
Yes.
Yes, they do. Right? So it would be nice to describe those with positions, velocities, and acceleration. But before we do that, it goes and comes back. It goes and comes back. Getting an idea of describing the going and the coming back, it might be good to label some of the parts of that motion. Okay? If we were to let's make a position graph. Okay, so position versus time for the tennis ball. What would that look like? Maybe what about a position versus time for the spring? So let's say this is the spring. Right? So I let go. What's it doing? It's bouncing up and down, right? So where's its position? This is hard. Right? So you gotta, so it's like where my finger is, and then if we want to do position, oh good, I did it down lower. Okay. If I do it down here, and I was gonna move it across like, yeah, do this. Right. So if I did position versus time, it would be where the mass is as I'm going across. If I walk across at a steady pace, it's doing that. And what was it looking like? Sort of like that? Okay. What would a tennis ball look like? And I need like a board right here. But if I throw the tennis ball at the ground, okay, and then it comes back up in my hand, what's that one look like? Same? Well, okay, it might start at a different location, okay?
There should be like a sharp net. Goes faster, it's more.
When it throw the tennis ball down, it goes faster, right? Where's it going its fastest?
At the bottom.
Right before.
At the bottom, right. So it goes really fast. Then what happens at the bottom? And then what? Does it just sit there on the ground?
Goes up.
And it turns around and goes up. Between the going down and coming up, is there a lot of time or a little time?
Little.
A little time. Yeah, so very quickly, if I, like, do you mind if I do this on the table? So we watch out. Yeah? Look, it doesn't like spend a lot of time down here, right? Most of the, and where's it going slow? Well, back up, or it speeds up. Once I throw it down, it speeds up on the way down. It then quickly turns around, and then it slows down. Speeds up on the way down, quickly turns around, then I throw it back down again. Yeah? Like that. So the position graphs look pretty different, okay? But they repeat. So if we wanted to think about parts of the motion that we could label to describe it, okay, what jumps out? What sort of, if you wanted, well,
Height over time?
so,
Where the
yeah,
springs
okay,
are.
so the height is changing over time, okay? Are there some ways that we could label this graph and talk about certain, oh, hang on. So I can take the spring and I can do this. I can say, well, I'll pull it down here and it goes up and down and up and down. And it goes up and down between these, between here and there. Yeah? Or I could do that, right? Now it's going up and down. Is that the same motion as the original one I did?
No,
What's different?
it's strong.
It's stronger. What part of it is stronger?
Position.
Position? What do you mean by
The distance
strong?
of position of separation.
Magnet.
The, what?
The difference of position of separation.
The different, oh, what separation? Separation of,
I'm just saying, there's a high piece in both views.
the peaks are different, right? The peaks are higher, right? So if I do this, well, let me see if I can get it. Yeah, so it's going down to here and up to there. The difference between the peaks, if this is position, maybe measured in meters or centimeters, this one goes a certain number of centimeters. This one goes more, right? So the difference from the peaks to peaks are higher. So one of the ways we could classify the motion, we'd say it's an oscillating motion, but it has the difference between the peaks and peaks is more. Often we'll call that an amplitude, right? So we could say here, we'll say here's the middle of the motion, and we could say this is the amplitude. Something like this, there isn't quite a middle of the motion. But you can imagine, throwing a ball down low or throwing it up higher, and these being higher or lower, and you could call that an amplitude. There's another part of the motion that we can use to describe it. Okay? It's, besides the going back and forth like this, okay, I can do this with the spring. Okay? I can say, all right, I'm going to do this, and it goes back and forth, that amplitude, okay? Or I can do this. I can grab it here and say, all right, now it's going back and forth, but in the same amplitude. Are those the same motion? What's different?
Time frame?
Time, the frequency, it's going faster, right? This one is repeating its cycle quicker, and the other one was repeating the cycle slower. Okay? So that idea is called frequency. Okay? So there's, we can do this, we can say A is amplitude, okay, which is the center to peak difference. The other thing we can do is we can talk about, well, we can talk about how long it takes. We could say, here, this is T, okay, which we'll say T, this is the period, okay, which is the time to repeat one cycle. Okay. So this would be, you'd measure this one in, say, meters, or whatever you're measuring distance. This one you'd measure in seconds, okay, which is, yeah, or whatever you're using to measure time. I suppose you could measure period in minutes or hours or something if it was appropriate. Okay. Then people said frequency. Frequency is another way of thinking about that time. It turns out that it's frequency. This is the number of cycles per second. Okay, and so if period is seconds per cycle and frequency is cycles per second, that's 1 over the period, right? So frequency is equal to 1 over the period. You know, I just said, period is time to repeat one cycle and you measure it in seconds. And then frequency, we said it was cycles per second. If you're doing dimensional analysis, it turns out that cycles doesn't count, okay? So if you said the period is so many seconds, frequency is reciprocal of the period, okay? Then it's just per second. Okay? So when you're doing dimensional analysis with your formulas, you want, you'll think about frequency as just per second. But you'll know that it's talking about cycles per second. And period is the time for a cycle. Okay? So all of these things have a period. All of them have an amplitude. Okay? Any oscillating motion you'll be able to talk about in that way. But some, they're just gobs of different ways that things could repeat. Okay? But I'm going to put this in the most pragmatic, straightforward mathematical way. If we wanted to describe something simple using some simple functions, okay, like here, when we described motion in constant acceleration motion, we used the formulas that we had were for a straight line or for a parabola, okay? And it turns out that those are, as far as mathematical function goes, they're pretty simple, basic ones, okay? Do we know of a pretty simple, basic function that repeats?
Time what?
Time? What's that mean? Time is a thing we can graph. What functions do we know? Trig functions like sine and cosine. Do they repeat? Yeah. In fact, what do they look like? Look kind of like what happened with the spring, right? And it turns out that if if there is a certain special kind of motion, okay, then it will repeat like a sine or a cosine. Okay? So that is called harmonic motion. Okay, and that means the x versus t, position versus time, looks like sine or cosine. Okay, so it does the back and forth like that. Okay, so you would say, this motion with the spring, okay, it turns out that it is a harmonic motion. Okay, and we'd say this motion with the ball is oscillating motion, but it's not harmonic motion. Okay? Now, what we're going to be studying is simple harmonic motion. Okay? And when we did this kind of constant acceleration motion, well, one of the simplifying assumptions that we often made was that there was no friction, right? That things would continue on at that acceleration or at that velocity or something. It turns out that the simple in simple harmonic motion means that we will approximate it as if there's no friction. So that the motion, if I pull down the spring and let go, it repeats and it goes back and forth forever. Now, do springs really go back and forth forever? No. Turns out there's friction with the air and there's friction with the spring compressing and coming back, that it doesn't completely, in fact, right now it is slowed down to stop, right? So we go, that wasn't really simple harmonic motion, because simple harmonic motion goes on forever. But you could say, we will approximate it as simple harmonic motion for the first, maybe 5 or 6 cycles, and then maybe later on we can, in fact, tomorrow, okay, we can study damped motion that dies back down. Okay, but simple harmonic motion is a good first approximation. Okay, cool. So you might think, well, what's special about simple harmonic motion? What is the thing that it needs? That causes it? If you were to have a bunch of different motions, and you go, all of these oscillate. I don't have the graphs, and I want to understand what causes the harmonic nature. Okay, it turns out that what causes it is let's think about this. The spring gets pulled down, okay? And when it's pulled down like this, okay, when the mass is down here, which way is the spring pulling?
Up.
The spring is pulling up, right? I'm holding the mass down, but the spring is pulling up. And the further down I pull it, if I hold it down here, is the spring pulling harder or weaker? Harder, right? So I go to this position, okay? This position here, where I've got the, well, now the spring is pulling up, the gravity's pulling down, and the net force on it is 0, right? If I lift up, which way is the net force? It's down, right? Because now gravity is pulling down on this, and the spring's pulling up, but the spring's pulling up not as hard. If I lift it up even further, okay, which way is the net force? Down. Is it bigger or smaller than it was here? It's bigger, right? And so it turns out that the further you are away from equilibrium, the bigger the force is, okay? And so we'd say, that's a restoring force. If that restoring force is linear, okay, if when you pull down twice as far, it pulls back twice as hard, okay, then you get the simple harmonic motion. Okay? So we can say So the simple harmonic motion is caused by a linear restoring force. For a spring, what was the force on us that a spring produced? You probably ran into it in 114.
Constant times position.
There's a spring constant K. Is the force constant? No, the force is not constant. So how does the force behave?
Changing position times the
It's
constant.
according to the position. So we'd say F is equal to, sorry, what was that? No, you said something, and I couldn't hear it. It was some K. Wow. The
Just
mu
KX.
K is the coefficient of kinetic friction.
Mhm.
Right. But
KX
there was a K associated with the spring
times X.
times X. Yeah? Does that look good? No, what's wrong? It's what?
Negative.
Is there a squared?
It's a negative
It
sign.
turns out that there isn't a squared here. Okay. But it's in the opposite direction, right? So when you, where's my spring? If I pull down, right, so my pull is, if I displace the spring this way, if I change its X in the downward direction, the force is in the upward direction, right? And if I had a spring I could compress, if I compress it, it would push back in the other way. So the direction of the force is opposite of the way I change it. So perhaps let's say minus kx, might even say minus k delta x. Okay. Where you could say delta x is equal to x, wherever my spring is, minus x equilibrium. This is where the spring it's sort of its rest position. Okay. So if I had a spring that looked like this, okay, and it was a stiff spring, and I do something like, and say, all right, it sits here, this is x equilibrium, and over here might be x, okay? So if I pull this way, then the force is back in that direction.
Is that OG? Is that OG?
Force in the spring goes like that. If I push the spring this way, then the force goes back that way. Force is always the other way. Okay? If my spring is hanging, then it's the same analysis that we talked about before. It'll hang at a certain equilibrium position. If I pull down, it pulls back. Okay? If I lift up, then gravity pulls down, but the gravity, the difference between gravity and the spring gets bigger and bigger the higher I lift it up, because the spring is pulling up less. Okay? And you end up, in both cases, you get a linear restoring force. And so you get that the mass on the spring does that. So, I ran out of room that way because I don't want to erase that. So I'm going to come back over here, and I'm going to say,
Well, aren't you going to put that on canvas?
I am.
Yeah.
Is everybody done with that? Everybody's done with that? Okay. And I will put it on here. It's what?
Is that the arrow, the spectral rest? If you rest, spring x equals.
That's in a spring's rest position. So I'm trying to label this x equilibrium is where the spring sits at rest. Okay?
That's not like an arrow. It's hard. Better arrow. There you go.
Better?
Yeah.
Thank you. I tend to get caught up in what I'm doing and let me know if it's not readable. So.
And is that simple harmonic motion case cause not case?
Better?
Is that N or U?
Where?
CANSED.
Yeah? Do you put little like wings and stuff on it? No, it's, seriously, I had to look, and I'm not good at this, but I've had to learn to try to write things clearer, and it's hard, okay? Especially with chalk and whiteboard stuff and things like that. So let me know when I'm messing it up. Okay. So now, we could say, all right, here's x, here's my x equilibrium, right? And I start at some certain position, okay? And then the object moves back and forth, okay? So if I start at up here, I would expect it to move like this. Yeah? And these should be horizontal. Okay? And this should be a sine or cosine. What I drew, is that if this is time, and this is 0, is that a sine or a cosine?
Cosine?
It's a cosine, right? Because cosine of 0 is 1, right? Cosine of cosine of pi is -1, right? And then 2 pi is back to 1, right? It repeats, yeah? Or cosine of 0, 180, 360 degrees, right? Okay? Now, this position, so we might say, x is equal to cosine of something that involves time, okay? Now, it's not going back and forth between 1 and -1. What's it going back and forth between? X and negative x? Well, yeah, okay, so this is, x is, if we say x is the label for this axis, okay, and it's going positive and it's going negative, but what position up here is it going to? And what position down here if we go back and look at the way we were labeling things? The amplitude, it'd be the A, right? Because we're starting at the amplitude, and then we're going down to -A, and it's if we go, this is the distance from the center to the peak, this is the amplitude. So we'd say, this is A cosine, okay? Well, now, it repeats when? It repeats, let's see, so we've got something here in the cosine, and when t has gone as long as a period, it repeats, right? Okay? And cosine repeats for this book, and everybody who does physics with simple harmonic motion, it turns out that the easiest sines and cosine functions to use are the ones that are in radians, okay? Which may mean that when you're dealing with a lot of this stuff, you may need to switch your calculator mode to radians when you're dealing with the sines and cosines in harmonic motion. So in radians, a repetition is 2 pi, right? Okay, and whatever this is doing and the way we talk about it, a repetition is 1 period, 1 capital T, okay? So when time has gone by through a whole period, okay, then what we want is for this to have gone through through 2 pi. Does that make sense? Okay, when time has gone through 1 period, we want the thing that we're passing to the cosine to be 2 pi. Okay? Well, we can do this. We can say that frequency is equal to, well, how do I write it over there? Frequency is equal to 1 over the period, right? So, frequency times the period is equal to 1, right? And what I want is something that when a whole period is gone by is equal to 2 pi. So I could say, well, 2 pi f t is equal to, well, 2 pi, right? So this is, when a whole cycle has gone by, this would be, well, this relationship is true, okay? And so then if I said, well, this is equal to 2 pi f t, the time, when a whole period is gone by, that period times f would give us 2 pi, which would mean the cosine is repeating. When this is 2 periods, I'd have 4 pi, the cosine would be repeating, and so forth. Okay? So it turns out that this formula, okay, gives me the position function. Okay, I can say the frequency is something constant, the amplitude is something constant, and if I knew that the mass in the spring was behaving this way, it had a certain frequency, it had a certain amplitude, I could plug in the time and it would go like cosine. Seem okay? Cool. It would be nice to then talk about velocity and acceleration. Seems like it might be hard, okay? Because, yeah, velocity, back when we were thinking over here, velocity was the slope of the position graph. What's happening with the slope of the position graph? Well, here, the slope is 0, so we'd expect the velocity to be 0. Over here, the velocity is negative, right? Because the slope is negative, and it's pretty big, and then it slows down to 0, then it gets positive, then it slows down to 0. If I were to graph the velocity here, okay, I would have something that starts off at 0, goes negative like this, turns around to 0, negative down here, turns around, comes up, hits its maximum, this positive value over here, and turns around. The velocity is going to look something like that, which also looks, well, this doesn't look like cosine. What does it look like? Sine, almost. Looks like minus sine, right? Because it goes negative first, then goes positive. Okay? And you go, gee, why is that? I might need some help for this.
You're the ones to help.
Would you like to come help?
Yes,
Yeah,
I
sure.
Yeah, come up now. You're going to volunteer people. Get up here. You are?
Nathan.
Nathan? Okay, hey Nathan. And what I want you to do is I'm going to hold the bicycle wheel,
Okay.
and we're going to see, I've never done this before. Okay, but don't worry, you won't get hurt. Okay? So what you're going to do is get this going at an amplitude that matches the height of the bicycle wheel. Yeah, so hold that and wait just a minute because I want to do something else. I'm gonna put blue tape along the wheel here.
There's no tape right there.
Is there? Yeah, but it's on the inside. I want it on the outside, okay? And I want to, no, that's okay. Well, here, no, I want it obvious. Thank you. That'd be great. I'm gonna go right around like this. So you can see the blue tape here?
Yep.
Okay? And so here's the middle. Now go ahead and pluck the mass on the spring and just bring it down here to the height of the wheel. When you let go, it should go back up to the top of the wheel. Does it do that, roughly? Yeah. Roughly?
Yeah.
Good. Now I'm going to start spinning the wheel, and I want to get it so this is hard. I was do you notice this is bouncing up and down, okay, and the tape is also bouncing up and down. If you look at the vertical part of it, it's going up and down. And if I get it, I was trying to see if I could get it so that
There
the
you go.
tape, did I get it? So the
Yeah.
tape is following the mass, right? And it turns out that the mass is bouncing up and down like sine and cosine, right? I think that's maybe as good as we get. Thanks, that was tough. Okay? And the tape was bouncing up and down, the mass was bouncing up and down, and they were in sync with each other, right? Which means we would actually expect this. If I were to say, if I said, all right, this is an angle, okay, and I'm going around and I'm repeating, okay, this is circular motion, and we could say, all right, the position of this, okay, we could say this is, if I measure my angle from here, we could say the position of this is the radius of the wheel times the cosine of whatever this angle is, right? And so if the angle is 0, it's going to be the radius of the wheel up here. If it's 90 degrees, it's going to be the position, the vertical position would be 0. If it's down here, it's going to be negative the radius of the wheel, and so forth, right? Okay? And so we can say, the vertical component of this gives us the position of the wheel, and it matches that position over here. And we've already seen this situation. When we talked about circular motion, we looked at, well, what was the position of a particle as undergoing circular motion, and we could describe it using actually the same function that we had right here. And we then looked at, well, what happened with the velocity, okay? Well, it turns out that when we did this, I'm trying to get my timing right, okay? When we come back over here and we do circular motion. You go back and look in the book, and the book says, we said the circular motion is r cosine omega t. Yeah? Okay? And then, so x is equal to this. V was equal to minus r omega sine omega t. Yeah? Okay? And A is equal to minus r omega squared cosine omega t. So we already did this. If you don't remember how this worked, go back and look at chapter 7 or 8, okay, where it talks about rotational motion, and they go through where this all came from. But the beauty of this is we go, hey, we've got some functions that look just like this. We have something that's got some constant, and then we have and then we have some sort of thing in here times the time. And this makes sense as an amplitude, right? The radius of the wheel in circular motion is the amplitude of how the position is changing, okay? This is a velocity, okay? And it turns out this makes sense too. So by analogy to circular motion, by saying that, hey, the fact that this behaves like a cosines and sines and follows what's going on in circular motion, we can then say, well, the velocity and the acceleration are going to behave the same way, right? In other words, if we were to look at the vertical velocity and acceleration of the blue tape here, right? If we were to say, you know, how is it moving, and it's following that mass, then whatever this one's velocity is, so is that one. Okay, so what we end up with over here is that this ends up being equal to a 2 pi f sine 2 pi f t, okay, with the minus there. Okay, as we described, and the acceleration ends up being minus a 2 pi f squared cosine 2 pi f t. Okay? And good. Notice that this acceleration is opposite the way the way the position, say initially is positive, the acceleration is negative, right? So if you say force is mass times acceleration, the mass is constant. The force is in the same direction as this acceleration. So what it says is that when we displace it this way, there's a force pulling down, okay, pulling it back towards the middle. When it gets down here, there's a force pulling it back up. Seem okay? Okay, cool. So we got equations of motion for our simple harmonic motion, and we've got, in terms of our amplitude and our frequency, the other thing is it sort of hints that omega is equal to 2 pi f, okay, and, which is, this is typically called the angular frequency. It turns out your book uses these formulas a lot. On the formula sheet, I have listed these formulas, okay, only with the A's, okay? They're the same thing, okay? If you, 2 pi f and omega are the same thing. Okay, so now I gotta go back here because I ran out of space. One of the other things I can talk about, okay, with this motion, we've talked about the position, acceleration, velocity, amplitudes, that sort of thing, okay? But you can also talk about what's going on with the energy, okay? So if we have something like our mass on a spring, okay, so mass on the spring, okay, energetically, what's going on? What sort of energies are present?
Kinetic and potential.
Kinetic and potential, right? So we have kinetic energy due to what?
Gravity. Oh, no.
What is kinetic energy?
The motion. Acceleration. acceleration.
Motion, right? So the motion is the spring. Wait, the motion is the mass going up and down. Spring is pretty lightweight. We're going to assume that the spring is negligible mass, and this is pretty heavy. This is 400 something grams. This spring itself is maybe 50. Okay, so it's not too, and I'm grabbing it halfway through. Okay, so it's not too bad. So, so the mass is moving. The kinetic energy due to a moving mass is what?
Is it
The equation?
Yeah.
1/2
1/2 mv squared, right? So we can
That's
say
what it
that
is,
the
right?
energy is
Seem
equal
like
to
a trick
1/2
question, like, it can't
m
be that,
v
okay?
squared, okay? And then, okay. We talked about the mass going up and down like this, but if we had a spring that could be stretched this way and compressed, the potential energy due to stretching and compressing the spring is what? Do you remember the potential energy for the spring?
Light and gravity.
Turns out, somebody was saying, there's a squared thing with the spring constant. There is, but it's the potential energy of the spring. So that'd be plus 1/2 k x squared. Okay? Okay? So this is the total energy, okay, of the mass and spring system. And if as it's bouncing around and going back and forth, you can think of it as trading off potential energy and kinetic energy. It's when its amplitude is high, its velocity is 0. When its velocity is high, its amplitude is 0. And the two of those end up adding together, and the energy stays constant. It trades off back and forth between being potential and kinetic energy. We can then say, well, if E for the system is constant, then we could say E, the energy of the system, is equal to, well, at the time when the velocity is at the maximum, the position is 0, or its displacement is 0, right? And so you could say, well, this 1/2 kx squared term would be 0, but you could say E is equal to 1/2 m v max squared. Or you could also say, well, then when the velocity is 0, it's stretched the most. You could say that's the same energy as 1/2 k x squared. You can cancel out the 1/2s. And then it turns out that because we know the equations of motion, we can say, all right, we know what this V max is, right? This V max is equal to, we'll say this is A omega, or we'll say it's, we'll do it that way. We'll say M V max is 2 pi F A squared, right? Times, well, that's its, when this is at its maximum, the velocity is going to be 2 pi Fa, right? Okay, so V max would be 2 pi Fa squared. And then this is going to equal 1/2 k, well, x max squared. X max is just A, right? A squared. If I distribute all these squareds, okay, what I end up with is that I canceled out the 1/2 up there. It turns out I can cancel out this A squared and that A squared, and I end up with 2 pi F squared is equal to K over M, okay? Or I can say F squared is equal to 1 over 2 pi squared K over M, okay? or that F is equal to 1 over 2 pi K over M. Yeah? So it turns out that the frequency, how often this repeats, depends upon K, how stiff the spring is, and what the mass is. Okay? And so if you know those are things you could measure ahead of time. You could predict what the frequency of the mass and spring would be if you have a certain spring and a certain mass. It also says, if I make the mass bigger, what's going to happen to the frequency? It's smaller, right. So a heavier mass would have a smaller frequency, a lighter mass would have a higher frequency. Nobody uses this formula. Your book does, but everybody else in the world says, remember how we said, well, 2 pi f is omega? Okay? Everybody else is going to write it this. And, oh, sorry, I took the square root of this. I should be the square root of km. Okay? Everybody else is going to stop here and say, well, 2 pi f is omega, so they'll end up saying that omega is equal to square root of k over m. Yeah? Cool. So here's my mass on a spring. It's got a certain frequency. Oh, notice it didn't say that the amplitude changed the frequency. So I could say, do this, okay, or that. Those all should be about the same frequency. So those are some predictions. It also said if that mass is smaller, it bounces faster. Notice if I just take the spring and pluck it like that, it bounces faster. In fact, I should have brought a smaller mass in. But if you do a smaller mass, it goes up and down a lot quicker. Okay? You can sort of think about it as the stiffer the spring, the quicker it goes, because there's more force pulling on things. And the heavier the mass, the slower it goes. Okay? Because it's harder to move up and down. Okay. What about the pendulum? If I take the mouse and do this, simple harmonic motion. Well, we got to see if we've got a linear restoring force, right? If we've got a linear restoring force, then it ought to be. Okay? And so, let's look at the pendulum. So, pendulum has some sort of mass, some sort of lightweight spring, and some angle theta, and you lift the pendulum up and it goes back and forth. Certainly it has a restoring force. The more you pull this way, it gets pulled, well, you pull over here, it gets pulled back this way. You pull over here, it gets pulled back that way. Yeah? So the question is it linear? If we look at a free body diagram, we could say, well, here is the weight, which is equal to mg, okay? And we say here is the tension going like that. And then we can say, well, this weight we can break into two parts. We can say here's a vertical component, say mg cosine theta, okay? And then this part here, we'll say this is mg sine theta. Okay? So that's the part of that's what's pushing the ball back towards this direction. Yeah? Okay? And it's related to theta. As theta gets bigger, okay, then the force gets bigger. seem okay? But it's not linear, it's mg sine theta. And you go, sine isn't the same as a linear function. Okay? So you go, well, in general, okay, a pendulum is not simple harmonic motion. Okay? So if I take something like this mouse and I lift it up like this and I go, ah, look, it's going back and forth. Turns out that's not simple harmonic motion. Okay? But pendulums are often used as an example of simple harmonic motion. Turns out, okay, and this is kind of a cheat, okay, but it's, sometimes you do problems approximately because they work out, okay, and you can get close enough. It turns out that if you move it just small amounts, like this, back and forth, so the angles aren't very big, it's pretty close to simple harmonic motion, okay? And essentially, so remember, we're looking for a restoring force that is linear. The further you move it away, it's just a constant multiple. The force coming back is a constant multiple of how much you moved it away, okay? Well, if you look at sine theta, if you were to say, here is, I'm sort of doing something like this, only with theta being pretty small, right? So here is my right angle. Here is, say, L, the length of the pendulum, okay? And this is, we'll call this S, the amount that this is vertical, S is this distance here, okay, that you've moved away this way, okay? Well, it turns out that, well, sine theta is equal to S over L. And let's see. This isn't really how far we moved it. We really moved it along an arc like this, right? Okay? Well, it turns out that for angles that are small, that little arc that we moved it is approximately equal to that, okay? For angles that are big, right? So if we have this is theta, here is L, okay? And our right angle goes like, oh, that's horrible right angle. Our right angle goes like this, and the way that we got there was like this. It turns out that these two are not equal, okay? But if you get them really close together, the paths that we take are pretty close to equal, and you can say that is sine theta is equal to S over L, which is approximately equal to the distance that we displaced it, okay? Yeah?
What's S?
S is this distance right there.
What's the abbreviation?
You know, we often use X and S. We often use S when we're moving along arcs of circles, and I don't know. I don't have an abbreviation. We don't have enough letters. Okay. Your book uses S as well, and again, I don't know. Okay. So then you can say, well, this restoring force is equal to mg s over L, and S is the distance, S is approximately equal to the distance we displaced it. So it is equal to some constant times the amount that it went. So it's approximately a linear restoring force as long as we displace it through small angles. Okay? So now you can say, well, we could go back through the whole derivation of the maximum and that sort of thing. But we could say this plays a role like K, okay? And we could then say that the kinetic energy formula is still the same, okay? And so then we could say if this is like K, if K is kind of like mg over L, okay? And then in the kinetic energy formula, m is still m, okay? Then omega should equal the square root of the K-like thing, the square root of mg over L, all over m. Cancel that out, and you end up with omega is equal to the square root of g over L. Okay? And so that's the frequency, the angular frequency of a pendulum if you displace it a small angle. Remember, if you displace it a large angle, it's not harmonic. So there's one more, and I'm going to do that even quicker because I want to play with it. The other thing you might have is yeah.
Is it harmonic or is it not harmonic, or is it just not simple harmonic?
It's not harmonic. Okay, it's not, the question is the pendulum harmonic or not simple? Okay, it turns out it's not harmonic. It's an oscillating motion that's not harmonic if you do it through large angles. It's only in the small angle that it gets close to being harmonic.
Is that because it also rotates to the x and z axis, like in a circular motion? Because isn't that what pendulums do?
It definitely does do that. I don't know if that's, I'm trying to go, would that require it to be like that? I'm thinking, you know, maybe if you fixed up the restoring force, you could get simple harmonic motion even though it moved like that. But at least with just gravity, you don't get simple harmonic motion for large angles because you end up with that, you know, the mg sine theta. So not only can you make something like a pendulum with a mass concentrated at the end, you can make a pendulum out of almost anything, right? You could, excuse me, let me find something odd shaped and safe to pick up. Oh yeah, no. Yeah, scissors, okay? I could say, I'm gonna make a pendulum out of scissors. And I'm going to hold it like this and swing it, and look, and see it oscillates, it goes back and forth, right? So we call this a physical pendulum, okay? So a pendulum has the mass all concentrated at the end of the string. A physical pendulum has the mass distributed however, okay? So if you displace your physical pendulum, okay, well, you've got a situation like this. This is, oh, that's a horrible scissors.
Those look like
I don't know. Okay, that's horrible. Okay, but I'm going to suspend it from here, okay, and it's got a center of mass somewhere, right? So you go, it's got some sort of center of mass. Okay, and we'll call this distance, I'm matching your book's definition, d. Okay, so that's the distance between where we're suspending it in the center of mass. Okay, now as it rotates back and forth, okay, it does so according, well, you're rotating it about a center, okay, and now, do we have a linear restoring force? Well, it turns out, well, we do, okay? When we pull this back, well, it's the same situation as the pendulum. When we displace it, we have a gravity pulling down, but the component that's going back that way would be mg sine theta, okay? However, the proper way to look at this, we've got some object that's spinning around this. The proper way to look at it is in terms of rotational variables, in terms of a moment of inertia, okay, of something rotating around some center, and a torque that's pushing it back towards the middle. And so okay, so we could say, all right, when we displace this, we have a force that's pushing it back towards the middle. Okay? We could say, well, the torque is equal to the force pushing it back to the middle, which is mg sine theta. Okay? And then times this d, this distance, right? Okay, and this force would be, the force is, if we displace it, so that we say, all right, this is d, this distance here is also d, and then we have a force going this way, which is mg d sine theta. Our torque is mg sine theta times d, right? And then we could say that when you twist this, and it's got this, it's restoring back, we could say that this is like the restoring force, and that mgd, this is like the k in that restoring torque, okay? And then when you go look at the energy, what's going to be involved with energy is not going to be the mass, but it's going to be 1/2 I omega squared, okay? And it's going to be the I that behaves like the mass. So what we end up with is that the omega for a physical pendulum is equal to the square root of mgd over I, okay, where this is the moment of inertia. Okay, and this d is the distance from the pivot to the center of mass. Okay. So here's what I want to do between now and 9 o'clock, and I think we should still be good. I'm going to give you a meter stick, okay? I want you let's say this is 0, that's 100 centimeters, this is 80 centimeters. Okay? So what you're going to do, I don't have a meter stick with me, I will get some. But you'll hold the meter stick at 80 centimeters and disturb it a little bit. Move it over. Don't move it a large angle, but move it over and let it swing. It'll go back and forth, and you should be able to estimate the period of the meter stick. Okay? I'm not going to get you the meter sticks right away, because the first thing I want you to do is predict the period of the meter stick suspended at the 80 centimeter mark. Okay. That's part A. Part B, measure the period. By swinging the meter stick. Okay, so you've got a lot of stuff up there. This obviously would be useful. Okay. Other things that are going to be useful is that f is equal to 2, I'm sorry, omega is equal to 2 pi f. Yeah? You may also want to review moments of inertia.
So U physical on.
What? Sorry. Sorry, this is a physical pendulum. Sorry, I was trying to move quickly so that you had things and we could have more time to work, but thank you for catching me on that. Physical, okay?
We don't need the mass of the meter stick or the displacement.
You might. Well, the displacement is sort of in on this, okay? I think you do need the mass of the meter stick. Let me go get some meter sticks, okay?
Your making is really tough.
Hmm?
Oh.
Liz, are you okay?
Well, if you had like, you had a pendulum, right? You drop it from a certain area.
Yeah, this is
It's
nice.
for her to gravity over the length.
Were you having fun?
Yeah. Oh my god, it was so funny when you walked back here and I realized that we could rotate this. That is so funny.
So it's obviously outside.
What happened? Swing damage.
I like this. Like, 3 hours of class, 1 5-minute break. Solid.
Solid. All we
All we
need.
need.
That is all we need.
Let's not sit down too long. But
Yeah.
Hey,
So fun.
You
Just
should
following
really
it.
learn how to warn a person.
so I got meter sticks. They all have a mass. Solve for it in terms of mass. When you've got it solved, I'll give you a meter stick and you can test it out. I'll come around and help.
What? Should we pause this?
Work together and